Welcome to Lecture 9.3 on Applications of Counting. We're going to use some of what we've been learning about probabilities and counting now to actually calculate some of those probabilities. And I'm going to use both the combinations and permutation shorthand, but also using the kind of hangman style to show you how to kind of logically figure out the problem as well. So today we're just going to, in this lecture, look at all kinds of word problems. Many of the probability problems involving dependent events that were solved with probability trees in Chapter 8 can also be solved by using counting principles, that is, permutations and combinations. Permutations and combinations are especially helpful when the number of choices is large. The use of counting rules to solve probability problems depends on the basic probability principle introduced in Section 8.3 and repeated here. And that is, remember that the probability of any event E is the number of events in E, the number of, outcomes possible in E, divided by the total number of outcomes in the sample space. So this is, again, our basic probability formula. So let's look at this. Let's look at this first example. From a potential jury pool with 1 Hispanic, 3 Caucasian, and 2 African American members, 2 jurors are selected one at a time without replacement. Find the probability that 1 Caucasian and 1 African American are selected. Okay. With combinations, again, here, the first question we're always going to ask, is this a combination problem or a permutation? Since if I pick 2 people, the order that I put those 2 people in, it doesn't matter. They're still on the same jury. So Bob and Ann is the same jury as Ann and Bob. Okay, so this is a combination problem. With combination, it's not necessary to consider the order. Simply count the number of ways in which 1 Caucasian and 1 African American juror can be selected. Now this is where I find like the little hangman method can come in handy. Okay, this is the shorthand notation, right? So if I want to select 1 Caucasian person, I have 3 Caucasians to pick from, and I'm going to pick 1. And then I need to pick 1 African American, and there's 2 to pick from, so I have the combination of 2 things taken one at a time. And so I can see that there are 6 different ways to select this specific jury pool with 1 Caucasian and 1 African American. If I'm doing the hangman kind of method, what I can do here is notice I put down a slash, an underline, for each choice I'm making. And so in this jury pool, I have 2 slashes because I want a jury of 2 people. And I want 1 of those people to be a Caucasian and 1 to be an African American. So this kind of helps me think through the problem when I use these kind of hash marks or underlines to kind of think through what each choice is doing. And I can see that there are 3 ways to pick a Caucasian because there's 3 different Caucasians, and there's 2 ways to pick an African American, and again, so I get 6 different ways. For the denominator, this is our sample space, right? We're picking 2 people out of 1 plus 3 is 4, 5, 6 out of 6 people. There's a pool of 6, and we're picking 2 of them. Okay, so I'm just going to have the combination of 6 things taken 2 at a time. And so my actual probability of this actual jury pool is 0.40. It's the event. There are 6 ways to pick 1 Caucasian and 1 African American, but there are 15 different total ways to pick a jury pool of 2 people. Okay, so it's helpful to me to kind of visualize the problem in this kind of hangman format, thinking about where each underline is a choice I'm making, it's a choice I'm making, and to think through what each of those choices represents. And sometimes there'll be multiple. Here we just picked 1 of each, but we could have multiples of that, and we'll see that in just a second. From a baseball team of 15 players, 4 are to be selected to present a list of grievances to the coach. In how many ways can this be done? Notice this did not ask us for the probability. It's just asking how many ways can we pick 4 players out of 15. So again, the first thing we're going to ask, is order important? If I rearrange the order of people, does that make a different committee that's going to present grievances to the coach? Of course not. Think about the people that are going to be in the office when they're speaking to the coach. If I put them in different seats in a different order, it's not a different 4 people. So again, this is a combination problem because order does not matter. It's the same people. Okay. So this is straightforward. We've got 15 people. We're taking 4 at a time. So this is just the combination of 15, 4. And we get 1365. Okay. Now we're looking for a probability. And this is where it gets more confusing. And this is why it really helps me to use the hangman method that I've been talking about. One of the players is Michael Branson. Find the probability that Branson will be among the 4 selected. So I have 4 people to pick, right? I have to pick, we're saying that we want to know that Branson is one of them, but then I have 3 other people that I need to pick. It doesn't really matter who these are. We just want Branson to be one of them. Well, how many Bransons are there in the team of 15? There's only 1, okay? And then if I'm going to pick 3 others, is that a combination of 15 things taken 3 at a time? No. Why not? Because if I've already picked Branson, I no longer have 15 players to pick from. I now only have 14 left. Okay? So there's only one way to pick Branson. I need 30 others, and I've got 14 left after I've taken Branson out. And so this is how I'm going to figure out my event, or the number of solutions in my event, or the numerator. Since Branson must be one of the 4 selected, the problem reduces to finding the number of ways the additional 3 players can be chosen. There are 3 chosen from 14 players, and this can be done as the combination of 14 things taken 3 at a time. So the probability Branson is chosen is 364 divided by 1365, which is approximately 0.267. Find the probability that Branson will not be selected. Well, this is really simple. Remember, the probability that something won't happen is 1 minus the probability it will happen. This is the complement rule. So all I have to do is subtract the answer we found in B from 1, and I get the probability that he will not be selected. And obviously, since he's only 1 of 15, there's a much greater probability that he will not be picked. Okay? So in this problem, we actually had the hangman rule, but 3 of the things in the hangman rule, 3 of the blanks, were all the same. They were the other 3 players that we didn't care who they were, so to speak. All right, let's look at another problem that kind of gets a little bit confusing. A manufacturing company performs a quality control analysis on the ceramic tile it produces. It produces the tile in batches of 24 pieces. In the quality control analysis, the company tests 3 pieces of tile per batch. Suppose a batch of 24 tiles has 4 defective tiles. What is the probability that exactly one of the 3 tested tiles is defective? So this is good because it uses the word exactly, not the at most or at least, etc. Because remember, when we have those inequal words, at most, at least, etc., we have to change it into exact language so that we can figure out probability. So we're picking 3 tile. Oh, I'm sorry. So is order important? We're always asking this question first because we want to know if it's a permutation or a combination. Again, if I pick 3 tiles, tile 1, 2, 3, and then put them in a different order, 3, 2, 1, am I testing a different batch? No, it's the same batch that I'm testing, so order is not important. This is a combination problem. Since order does not matter, there are a combination of 24 things taken 3 at a time, ways to choose 3 different tiles. This again is our sample space. There are 2,024 different ways to pick 3 different tiles. So there's 2,024 different batches we could test of 3 tiles. All right. But in this specific, we want the probability that exactly 1 tile is defective. Let me move my pointer here. And 1 tile is defective, and 2 tiles are not defective. Well, how many ways can I pick a defective tile? So we need to look at the problem and figure out what data is in the problem that's going to help us with this. And notice that it says that this batch of 24 tiles has 4 defective tiles. So since I want to pick one defective tile, I've got the combination of 4 things taken one at a time. And if there are 4 defective tiles in the 24 tile batch, that means there are 20 non-defective tiles. So here I'm doing a multiplication principle. I have the combination of 4 things taken one at a time to select the defective tile. And since I want 2 to be non-defective, I have 20 non-defective tiles and I'm going to pick 2 of them. All right. So again, to me, the Hangman really helps me kind of think through the problem, where sometimes just writing down these combinations makes is a little bit more confusing. There are the combination of 4 things taken one at a time ways of choosing one defective tile from the 4 in the batch. If we choose one defective tile, we must then choose 2 good tiles among the 20 good tiles in the batch, and we can do this in the combination of 20 things taken 2 at a time different ways. By the multiplication principle, there are then 760 different ways to pick a batch with exactly one defective tile. And so our probability of this is simply this specific event, which is exactly one defective tile divided by the sample space. And we get an answer of a probability of approximately 0.3755. Let's continue on with the same problem with a different question. If at least one of the tiles in a batch is defective, the company will not ship the batch. What is the probability that the batch is not shipped? Okay. Immediately here I see the word at least, and so this is a warning sign to me that I have to change the language of this problem. If at least one of the tiles is defective, well, that means the probability that 1 is defective, or the probability that 2 is defective, or the probability that 3 is defective, right? If at least 1, that means 1 or more. So I really have to calculate 3 different probabilities: the probability that 1 tile is defective, the probability that 2 tiles are defective, and the probability that 3 tiles are defective. Now we already did the probability that 1 tile was defective on the last slide in problem A. So see if you can figure out that same way of what the probability would be if there were 2 defective tiles. So in that case, there'd be 2 defective and 1 not defective. Is that right? And then we'd have the probability of 3 defective tiles and 0 not defective. Okay, so I'm just going to walk through this pretty quickly. I suggest that you pause it and try to do these 2 problems. It's exactly like we did in part A, so you can rewind a little bit and see that again, and then calculate the probability that 2 are defective and that 3 are defective. And then hit play again. The batch will not be shipped if 1, 2, or 3 of the tiles are defective. We now need to find the probability that 2 are defective and the probability that 3 are defective. Because we already found the probability that 1 is defective in the previous problem, that's why we're not finding it here. So the probability that 2 are defective means that we have 2 defective tiles out of the 4, and we have 1 not defective tile out of the 20. And we get 120 for that. So the probability is 120 divided by the number of possible outcomes in the sample space. And then the probability of 3 are defective is the combination of 4 things taken 3 at a time. And of course, we want 0 not defective, so we get 20 taken 0 at a time. And remember, that just equals 1. And so here we get the probability of 0.0020. Now we want the probability that the batch is not shipped, so that means the probability that 1 is defective, 2 is defective, or 3 is defective, and that's just a sum of those 3 probabilities. Okay, and when we add them all together, we get 0.4368, approximately, because again, each individual probabilities was also a estimation. Okay. Part C, the same problem. Use the complement rule to find the probability the batch will be rejected. Well, we already know this because this is the same question as Part B. So we already have the answer that we just got in Part B, but this is asking us to find it in a different way. Okay? We reject the batch if at least one of the sampled tiles is defective. The opposite of at least one tile being defective is the none are defective. So let's find the probability that no tiles are defective. Well, this is pretty simple, right? We're going to pick 3 tiles and none of them are defective. So we know that there are 20 tiles, 20 non-defective tiles. So we're going to pick, this is just the combination of 20 things taken 3 at a time. This is our numerator in the probability. And so the probability that 0 are defective is 0.5632. But remember, this is not what we want. We don't want the probability that it will be shipped because there's 0 defects. We want the probability that it will not be shipped, that there's at least 1. So remember, with the complement rule, we have to subtract this number from 1. And here you can see we get the same answer, 0.4368, that we got in problem in Part B. The reason I'm showing you this and the reason the text is pointing this out is often when you're dealing with these at least or at most probabilities, it's often easier to use the complement rule. Because notice that in the last problem, in both these problems, B and C, we were looking at least 1 is defective. So that was the probability 1 is defective, 2 is defective, or 3 is defective. Well, it's much easier just to do one calculation where none are defective and then subtract that from 1. So the complement rule can really help you simplify the amount of work that you have to do. All right, this is a great series of questions and problems similar to what we did before to look at different ways of figuring out what are the number of outcomes in the event. So in a common form of a 5-card draw poker, a hand of 5 cards is dealt to each player from a deck of 52 cards. There is a total of the combination of 52 things taken 5 at a time, or 2,598,960 different possible outcomes for picking 5 cards from a deck. That is, of course, the number of different hands that we could have, or the sample space. Okay? So in Part A, we want to know what is the probability that we have a heart flush hand. Okay, so we're picking 5 cards and they all have to be hearts. Okay, well, how many hearts are there? There's 4 different suits. There are 13 hearts and we want to take 5 of them. So that's our numerator. The combination of 13 things taken 5 at a time. Because again, a hand of cards, it doesn't matter how you arrange them in order, you still have the same hand of poker, if you will. And so the probability of a heart flush is the number of events in our outcome, 1287, divided by the total number of outcomes possible that's given in the problem. Now it gets a little more complicated with B, because now in A we just needed 5 hearts. Okay, in B we need to consider a flush of any suit. Okay, it's really not that complicated, right? So the probability that we have a heart flush is here, 0.000495. Well, this would be the same as if we said a probability of a diamond flush, 0.000495. or a spades flush, or a clubs flush. So there's 4 different probabilities based upon the specific, what is it called? Oh my God, suit of each card, hearts, diamonds, clubs, or spades. But, so what we can do here is simply say, we can add all of those 4 together, or simply multiply this probability by 4 because there are 4 different suits. Okay. We could add them together, the probability of hearts, the probability of diamonds, the probability of clubs, the probability of spades, which they're all the same, so we can just multiply that by 4. C and D are going to be a similar thing. So let's look at C. See if you can try to do C on your own. You might want to do the 3-2 hangman marks, okay? A full house of aces and 8s. And specifically, we want 3 aces and 2 8s, okay? Well, there are 4 aces in a deck, right? And we want 3 of them. So we have the combination of 4 things taken 3 at a time. There are 4 8s in a deck, diamonds, hearts, clubs, and spades. And so we want the combination of 4 things taken 2 at a time, and this is our numerator. Again, our denominator is just the combination of 52 taken 5. And so here we get the combination, we get the probability of 0.00000, I think that was right, 923 approximately. But what if we want any full house? 3 cards of one value and 2 of another. Well, how many different numbers are there? Well, there's 13 choices. Okay. So that leaves 12 choices for the second value. All right. So here we would have 13 choices to get the first 3 cards from any number. And then once we have done that, we would get 12 choices to get the 2 cards from another number. Okay. So again, this is kind of like A and B. Here we were doing suits. Now we're doing specific cards. And there's 13 cards in every suit. So once we've picked which number is going to be 3 of the cards for a full house, like 3 aces in part C, then we have 12 left to pick the 2 cards. And so this is really important to see how this works, because we're doing 2 different combinations, 2 different numbers. There's a lot more different combinations. Aces and 8s, kings and 3s, kings and 8s, queens and 8s, etc. So you can see why there's so many different combinations. And so this, the probability greatly raises if we're doing any specific, not one specific flush, but any full house. Excuse me, not a flush, but a full house. All right. So this is a good problem to look at and pay attention to the details of how to calculate it, because the setup of these problems, once you've got the setup and understand what you're trying to look for, the hangman model or the combination model, it's just putting those into your calculator. But setting it up and thinking through what am I actually doing is the key challenge in these problems. A cooler contains 8 different kinds of soda, among which 3 cans are Pepsi, Coke, and Sprite. What is the probability when picking at random of selecting the 3 cans in the particular order listed in the previous sentence? Is order important? Well, notice that this problem says to select them in order. So I need to pick Pepsi, Coke, and Sprite. All right. Well, if I write this down, as a hangman, I'm going to have 3 underlines. The first one needs to be Pepsi. The second one needs to be Coke, and the third one needs to be Sprite. Well, how many Pepsis are there in the cooler? 1. How many Cokes are there in the cooler? 1. How many Sprites are in the cooler? 1. Because there are 5 other kinds. There's 8 different kinds of soda, and only 3 of them, 1 Pepsi, 1 Coke, and 1 Sprite, are there. So this is actually a really simple problem. Here's our sample space. Right? It's a permutation problem because order does matter. So we have 8 things taken 3 at a time. This is the number of outcomes in our sample space. But since each can is different, there's only one way to choose Pepsi, Coke, and Sprite. Again, if I did my hangman, there'd be one way to pick Pepsi, one way to pick Coke, and one way to pick Sprite. 1 times 1 times 1 is 1. So the probability in this problem is 1 divided by 336. This seems like a tricky problem because you have to pay attention to the detail. There's 8 different kinds of soda in there, and of those, 3 of them are Pepsi, Coke, and Sprite, and those are the ones you're picking, but you're picking them in a specific order. So again, the hangman would be really helpful here to see that. This last problem is a very common probability problem, and I hate this problem. And I'm just going to give you the formula at the end, but I want to explain it to you a little bit. But it's just not a big deal problem. It's an interesting phenomenon about how the probability goes up really high with even small groups of people, that there'll be two people in a group that have the same birthday relatively quickly. Find the probability that no two people among 5 people have the same birthday. Okay. The number of ways that 5 people can have different birthdays is 36. If I look at the first person, that person can have any birthday. As soon as I take that person's birthday out of the list, then I have 364. I could do this as a hangman, right? The first person has all of the whole calendar. The second person has all the calendar except for the first. The third has except for the first and second, etc. So each day we take out, we're going to go down by 1. Well, this is the same thing as the permutation, 365 taken 5 at a time. Okay, I like the hangman a lot, especially for permutations. The number of ways that 5 people can have the same or different birthdays is 365 times 365, right? These are all the different possible ways that they can be the same or different. It doesn't matter here, right? So we don't take them out. So the probability that none of the 5 people have the same birthday is the permutation of 365 things taken 5 at a time divided by 365 to the 5th power, or 0.973. The probability that at least 2 of the 5 people do have the same birthday. Remember, here we've done the complement, okay? So we need to subtract our answer from 1 because we found the probability that none of the 5 people, and we wanted to find that no 2 people have the same birthday. I'm sorry, we want to find the probability that at least 2 of the people. So this means that 2 or 3 or 4 or 5, okay? Notice that would be 4 different calculations. So by doing this complement problem, it is much easier to solve this, okay? Now here's a simple, here's kind of the simple formula for finding out about sizes of groups, okay? So the n in this problem represents the number of people in your group. And so if you get 1 minus the permutation of 365 people taken n at a time divided by 365 to the power of n, this will give you the probability that at least 2 people will have the same birthday depending upon the group size, and n is the size of the group. All right, this is the end of 9.3. Hopefully this has been helpful to you. These problems can be confusing. I think the hangman method can be very helpful of looking at what each of your choices is and to kind of rationalize and logic through it. Reach out if you need help.